Hey everyone. So in the last video, we talked about model theory, and I gave some intuition and motivation for what we'll be aiming to do. And we're gonna, in starting with this video and moving forward, try to get the ball rolling and try to start proving some things and developing, model theory itself. And in order to do that, um, the way this will work out is that our model theory will be developed within some logical framework. And we'll begin with, eventually we'll need to develop it in first order logic. But for the time being, we'll work entirely in, let me make that a little bit thicker. We'll be working in propositional logic. And the goal for this video is we probably won't even get to the model stuff. We just want to establish propositional logic, formalize it, so that we can begin working within it. Okay, so propositional logic is something I think pretty much everyone will be familiar with, and it is this is basically the Boolean algebra, where propositional logic will, and this is not. I'm going to give the actual definition right after this, but for the time being, this is just an intuitive definition. It will have propositions P and Q as an example. And these are variables that take on values of true or false. And then it will have logical connectives. And these here are the connectives. And these connectives are ways of taking two propositions and uniting them together to form a new sentence that has, that still, it's an operation on these propositions. Right? So it'll take in one or two propositions, and what it'll output is a true or false value. I won't going in, but I'm sure you've seen like truth tables and all that stuff for these. But let's run through quickly because these symbols may be foreign. So this is and. This is also called the conjunction. This is not, also called negation. This is or, also called disjunction. I'll probably be using a lot the words conjunction and disjunction for these as opposed to and or, because when you're speaking English and then you say you need to use conjunctions in sentences, it'll get confusing. So I'll probably be referring to this as conjunction and this as disjunction. Of course, we have implication. We have the if and only if, and we have the exclusive or. That's what these symbols mean. We'll probably not use this one ever, but it sometimes comes up in it's pretty useful to connective in logic, but for our purposes, it will rarely be useful to sort of when you're proving things that you want to be true. So it's rare that you would try to prove that precisely one of two statements are true. But anyway, it's much more frequently we'll be using an equivalence then. Anyway, none of that really matters right now. The point is, you've seen this before. This is propositional logic, and the way you would define these connectives, of course, is with truth tables. So what we'll be doing is going from basics and using like rigorous definitions to build propositional logic, and I'll give the rigorous definitions, but along the way, we'll make note that because we'll be moving from definitions that are the definitions we're choosing here are very wisely chosen because they'll make a lot of the proofs later on much easier. But we'll need to just intuitively check for ourselves as we're writing these definitions that they align with what we expect propositional logic to look like. Okay. So let's begin with a sentence. Sentences are kind of the foundational element of propositional logic. And so what I'll provide for you is defining a sentence. What we're doing here is we're creating a formal language that represents propositional logic. I don't know if that's something, this is something that some of you may have seen, some of you may have not seen. But the idea of a formal language is I'll give symbols, and I'll give you syntactic rules to arrange those symbols. So, for instance, English is actually an example of a language, right? Like, the point is we have letters, and those are the symbols I'm allowed to write. And then I have legal ways to arrange the letters together that form, words and sentences and all that. So what we'll be doing is sort of trying to build a language using these mathematical symbols. So before we do that, though, we need to run through what symbols we have. So sentences will come later. For now, these are the symbols we'll be using. So first off, we have sentence symbols. I want this to correspond with the colors I used on the last slide. And sentence symbols are basically just propositional variables, like P or Q. And the idea is, like I'm saying, when I make a language, what I want to do is basically, if we're talking formally down to like the set theory, I'm giving you symbols, and then I'm allowing you to form strings of, strings where you pick symbols, but I'm also going to tell you rules for what is and is not syntactically valid. But in that end, we want to write P implies Q, so we need variables in this language. So the rule is, together we'll specify some set of sentence symbols script S. And script S might be the set PQ, it might have more. We'll agree on what the sentence symbols are, and then we'll be able to use them when we're writing our sentences. That's important, right? Because we need variables. So that's one thing that will be in our language. The next thing is, of course, connectives. That was what I had on the previous slide, right? So this is lining up with what I just wrote down and what we understand propositional logic to be. And the connectives we'll be allowing are negation and conjunction. And that's it. You may be familiar with this idea that it turns out conjunction and negation are sufficient to write all possible connectives. And this isn't something we'll waste our time proving. It's not actually necessary to prove that. Ultimately, we're going to build propositional logic, and it's going to be what it's going to be. But thankfully, because not and are able to express any of the connectives, we won't need to do more than this. If you want to prove that not and can express any of the connectives, what you would do is, maybe this is something to think through. You have P and Q, you would write a truth table where you have P and Q, and then you'll have true, false, true, false, true, false, whatever. And there's this. The truth table looks like. I'll write this out just for the sake of understanding. So the point is, there's different combinations of whether P and Q could be true or false, and all of these could be either true or false. So that gives us 16 different possible connectives. And it might be worth trying, if you haven't seen this before, it might be worth trying to write all of the 16 possible arrangements of true and false on the right-hand side here for the conjunction PQ, only using ors and nots and ands. But either way, I won't go through the proof. It can be done, and thus it's not necessary to include any connectives in our language besides and not. And finally, and least importantly of all, I won't even try to write the word. We have parentheses. And this is just because we want to imbue our language with some meaningful order of operations, right? In theory, whenever we write a sentence like, for instance, whenever we write a sentence like P, not P and Q, we need to distinguish it between, not P and not P and Q, right? These are two completely different sentences with two completely different truth values. So we'll need to distinguish those, and so parentheses are completely necessary to include. However, we'll say that, if I write not P and Q, I really mean not P and Q. We'll say that, this is the same rule for the negative sign in This is the same rule for like the negative sign in just arithmetic, but either way, the point is we'll agree together what this means, but our language won't know, and so we'll have to develop syntactic rules that account for parentheses. In practice, though, we'll be forgetting about them, right? Like even as we do the proofs, I'll pretty much pretend parentheses don't exist, but it is worth mentioning that they are a foundational element of the language we're building. Okay, so these, a set and 4 symbols are all we need. That's propositional logic. So now, what we're going to do is come back to sentences now, and I'm going to define a sentence, and this is going to be a recursive definition, which makes sense because, right, if you have like P, you can make the clause P and Q. But if you also have not P, you could make the clause not P and Q, right? Like, or you could even, you could then have not, P and Q, right? So you can always take, if you've stuck connectives together, you can always stick more on to make a new sentence. So we'll capture this with a recursive definition where we basically say these are the rules allowing you to build new sentences out of old sentences, right? I believe this would be. I'm not entirely certain. I think this is legally, like, this would be a context-free grammar that we're building here, but it's not really that important because we won't need any of those definitions. We'll just define recursively to ourselves what a sentence is. So there's four things that make something a sentence. So we'll run through all of them now. So one is, and I'll just write down what they are. So for every sentence symbol, and then in gold over here, the sentence symbol itself is a sentence. So I could just say P, and of course P will have the truth value of P, right? So any variable can, and this is sort of the starting point. This is the base, right? Any variable is a sentence, and then we'll show that how to use nots and ands to form new sentences from the sentences we already have. So now, for any sentence symbol P, that's not even true anymore. If I'll write this as phi now, I'll let P be the symbol itself, and phi will be a sentence. So for any sentence phi, not phi is a sentence. And I put parentheses around it so that we don't confuse the order of operations. Like I said, it'll be in this definition, but we won't really need to think about it because we all know the order of operations of logical connectives. For number 3, if you have phi and psi as 2 sentences, then the following is also a sentence. Phi and psi. Okay. So this is what you would expect, right? Is that any variable is a sentence, and then given any sentence, I can negate it, and given 2 sentences, I can always take the conjunction of 2 sentences. Okay? And then finally, and I'll have to write this small probably, but basically this is just going to say that phi is a sentence if and only if it is a finite sequence of applications of 1, 2, and 3. So the idea is, this is important too. This is an if and only if, right? So not only can I make new sentences, I can always make a new sentence with a negation, and I can always make a new sentence by taking the conjunction of 2 sentences. The only sentences that exist are precisely the sentences that can be formed by beginning with sentence symbols and then taking negations and conjunctions, right? So there isn't some weird, like, okay, all this is true, however, close parenthesis, P not, that's also a sentence, right? This just rules out everything else. And that's important that, because if I didn't write 4, this is a good thing, this is a very common thing in math, but like if I erase bullet point 4 at the bottom, it would still be consistent with 1, 2, and 3 for everything to be a sentence, right? We definitely need the only if that says not only is this how you build sentences, but this is the only way to build sentences. Okay. All right, well, that's good. That's actually the definition of a sentence. And so now we have a syntactic framework of like what is a legal arrangement of symbols to make a sentence and what is not a legal arrangement of symbols. And we'll run through let's actually run through a brief example here just to elucidate what a sentence is, right? How this recursive definition works. So for instance, let's say over here that my sentence symbols are P and Q, okay? Then P is a sentence by axiom 1. I don't know if I would call it by bullet point 1. By point 1, P is a sentence. And by point 2, Q is a sentence. Also by point 1, Q is a sentence. Then by point 2, not P is a sentence. And also by point 2, not Q are sentences. Since P is a sentence, not P is a sentence. Since Q is a sentence, not Q is a sentence. And then finally, since not P is a sentence and not Q is a sentence, then not P and not Q is a sentence. And that's by, right, so this is application of 1, this is application of 2, and this is application of 3. And then returning to using 2 again, I can also always negate this. So since not P and not Q is a sentence, not P and not Q is also a sentence. So one thing we'll do for ourselves, for the sake of shorthand, is I'm going to define P or Q. Maybe I'll put that on the other side because I have more space. Or we'll go up. So I'm going to define that this is equal to P or Q. And you can check if you want. You can work out truth tables. But this is De Morgan's law that this expression not P and not Q is equivalent to P or Q. And like I said, you could work out De Morgan's laws, but that's actually not necessary in the proof, right? I'm sort of defining what or means, and I'm saying that or literally means this weird expression, not P and not Q. And it's thankful, you can if you look at the truth tables, you'll see that this corresponds to our intuition of what or ought to mean. So this is important because when I continue moving forward, and I'll probably rewrite this down as I talk here. But as we continue moving forward, we're going to want to use all of the strength of logical connectives to our advantage. So what we can do to that end is just define what we mean. So this is just all shorthand, right? So when I write P or Q, I actually mean not P and not Q. I should probably actually be using Greek symbols for this, so I'll switch to that from here on. So for phi implies, right, because these are just propositions, but I actually mean this for sentences, not merely sentence symbols. So for phi implies psi, I mean not phi or psi. And for phi is equivalent to psi, I mean phi implies psi and psi implies phi. So this is legal, and it's sort of, there's two things that we might want. At some point we'll be constructing like statements and axioms and whatever, and I'm gonna want to be able to use ors and implies. Like, I mean, math is built on implies. I'm gonna want to be able to use implies. So for this, to this end, this will be useful. However, when I'm doing a proof about statements, because the definition of a statement is recursive, I will necessarily have to use induction to prove something about a statement. And because of that, it'll be extremely helpful that secretly everything is only and not. Because that means in my inductive proofs, there will only ever be two cases, right? There's the case where, I'll prove almost everything I'll prove about statements will be inductive. And the way I'll prove it is, given a statement, if something holds for a statement, it holds for the negation of the statement. If something holds for two statements, it holds for the conjunction of two statements. Right? So it will radically simplify our proofs to only have to deal with not and and. So that's why there's sort of like this duality of the way we're setting it up. Is there's situations where it will be helpful to write down implies and the biconditional and disjunction, and there'll be situations where we'll wish that we hadn't. And so by defining everything in terms of and not, we can kind of get things both ways. Okay, so hopefully that made sense. And this is the syntactic definition of propositional logic. So I'll make a small note here of the distinction between syntax and semantics. And these aren't like precise mathematical. These aren't defined precisely mathematically, but this is helpful verbiage to have, because we'll be, this is a good framework. This is much more of a linguistic phenomenon than a mathematical one. But this is a useful thing to think about, because whenever we're dealing with a language, this is a useful question to ask. So syntax basically refers to what is said, and semantics is basically referring to what it means. So for instance, I might write down the statement implies S, or implies P, open parenthesis. And this statement is syntactically, I don't want to write that down, but this statement is syntactically invalid, right? Like the arrangement of symbols isn't even legal. There's other statements like this, like the statement not P, you switched to a different color, like the statement not P and P, where this statement will always be false. However, as far as we're concerned, this is a syntactically valid statement. Like, I can write this down, even if it's always false. At least it's a legal arrangement of symbols. So there's a little distinction there. And what we've done so far is this. So we've syntactically developed propositional logic. We've created a rigorous way of, given any sequence of and a string is just basically a sequence of symbols, right? So given any sequence of, or it needs to be finite too. That's important, right? So I have an inductive definition. So my statements can be arbitrarily long, but not infinitely long. But that's just a consequence of recursively defining something. So we've basically developed a rigorous way of saying whether or not something is syntactically valid. The next step, and the way logic is useful, is assigning a semantic meaning to these syntactic formulas we've built. And, we're at 20 minutes, so I'm trying to make these shorter so they're more watchable. But we'll stop here. And our goal for next time is like I said, is to assign semantic meanings to these syntactic formulas that we've developed. Okay, so I think that's it. Thank you guys for watching, and I'll see you next time.